tutorials on topics such as intracranial, EEG, FNIRS, so different modalities for recording brain data and how to analyze them, as well as more in-depth topics for analysis of the data. For example, deep learning for classification. So the idea is that we'll have these online sessions. So today is the first session, that's why it's in person. But the following sessions will be held online, so everybody could join via Zoom link. So these will happen approximately once every 3 months or so. And what we wanted to stress out here is that we want to make it community-based and community-driven. So Tan here has been really nice in setting up a Discord server where we could all communicate with each other outside of the conference as well. And what we want to invite you to do is to join that Discord server. You can scan the QR code that Tan has put over there. And
hopefully it's large enough.
Yeah. And basically what we'd really like to do is to set up a poll there about the types of topics that you guys could be interested in. So we could set up those tutorials around the topics that are actually needed by the community. All right. So as I mentioned, for today, we have a very easygoing first session just to try things out and see how it goes. And we wanted to focus on basic setups of working with BCI data using Python. We're going to look at loading, visualizing, and pre-processing BCI data. We are going to look into the basics of modeling with machine learning for BCI. And we're going to follow along scripts that use Python code to apply these modeling approaches to EEG data. And in a bit more detail, I'm going to work through my introductory slides. So this one is about the tutorial setup. In a moment, I'll talk a little bit about Python. I'm curious how many people here actually are familiar with Python already, or how much we may need to introduce it a little bit. Then we're going to have a little break, before which Tan is going to talk about the co-lab environment, and we're going to make sure that you're starting to get it running so that everything is ready for the actual practical side. And after the short break, we're going to go into the follow-along tutorial with data loading, modeling basics, classification with one of the simpler methods, but still widely used, called support vector machines. I'm sure many of you have heard it. We're going to talk a little bit about important concepts in machine learning, including overfitting regularization. And at the end, hopefully, there will be time to dip a little bit into the artificial neural networks. All right. So one of the things that's going to be important to talk about is the type of data we're going to work with today. And that's, as I mentioned, the EEG data. So these are publicly available data. So in case you want to continue working on it, or it's interesting for your research, you want to play around with it, you can find it online and continue doing things at home outside of this tutorial. So the link to it is in this corner. So of course you don't have slides, but we will share the slides. So you will have the link, you will have all these resources. We will set up a GitHub account and we'll share the link with everybody who's present here today. So you'll have these resources. All right, but the data set is called the Matching Pennies dataset. It includes 10 EEG channels, and those are the channels over the motor cortex. You can see my cursor, so I think these are just these 10 channels over here, somewhere around the motor cortex, because the data set involves participants raising their hand, either left hand or right hand, and these movements are performed on cue. So there are trials that performed correctly and trials that performed incorrectly. So there are 7 subjects in total, and the data set is in bits format. So I'm wondering how many of you are familiar with bits format? Oh, a lot of people. Great. Wonderful. So just a little side note about the bits format. So bits is it's a great thing. It's an upcoming standard format for reproducible neuroscience that is very popular in fields that include fMRI. It started with fMRI, I think, but it's now expanded a lot, and they have support for all other common modalities of brain recordings, MEG, EEG, intracranial EEG, and so on and so forth. The good thing about it is that it has a very rigid standard structure, so all of the data that you can have, you can put into a very specific structure, and anybody can work with it using existing tools, existing packages for Python and MATLAB, and they can access your data easily, read your data easily. So the structure that it supports includes a lot of meta files. So per data set here, you would have a number of meta files that contain information about participants. So you'll have a participant table that contains information about what each participant, important information about each participant. You have so-called sidecar JSON files. These just contain additional information necessary to read your data. It contains a README file that explains what is in the data, and it contains the task explanation. Then per folder, you have a stimuli folder, you have sometimes the source data, you have code optionally, and then an individual folder per subject. So the data within each subject's folder is also standardized, and for EEG it comes in the brain vision format. I'm not sure if you are familiar with it, but it's also very easy. It includes metadata in header files and marker files, and the binary file for the actual EEG recordings. And the idea is that if, as a community, we move towards using a standard format for sharing our data, it makes life much easier, because if you wanted to analyze somebody else's data and it also comes in bits format, you already know what to do with it, because you're familiar with the structure. The structure is always the same. So I encourage you to check it out, look at it and see whether you can find space for it in your practice, because it would be really great if as a community we move towards using this. All right, so as already mentioned before, we're going to work in the Colab environment, and here is a link. Currently in Tan's personal GitHub, but if things go well, we will set up the BCI Society GitHub, and I will share all the materials there. So you can follow this to open the notebook.
One moment, please.
In a moment.
That is also set up.
So if people follow the link, will they find themselves in the Colab already?
Yes, so this will send you to, okay. So this will send you to GitHub, where you will see a link to open in Colab for the notebook. And maybe we can try following here?
Of course.
And this will set up a private instance for you, so other people won't be seeing your changes, so that everybody can follow along simultaneously.
So
click on the notebook.
Yep. All right, and I guess.
And above. Move above. Okay. And open the Colab.
Oh, of course. So yeah, for people who are blind like me, there is a little button over here. If you press tutorial BCI meeting and then the IPython notebook, and if you click that button, that should take you to the private instance of the Colab environment.
All right. Do you want to continue?
Yeah, I can quickly finish up the slides. Or do you want people to already start downloading the data?
I think we can go with yours for it.
Alright, sure. Okay, was everybody able to follow along and open this I took some notes. Is that a question?
Yes, just generally, do we have any power class here?
Yes, that's a bit complicated.
Thought so.
We really try to arrange some, but apparently that's really not possible. Yeah, there is a power bank, an extension here, so you're welcome to try and tap into it. I cannot move it very far though.
There may be some on the ground.
Yeah.
Those look like.
Oh yeah, so I see there are some
Yeah.
something. There's a thing over here. So you're free to come at the front of the class. I'm sorry. Just sure.
Is that one over there?
That didn't look like something you could. Oh, yeah. Yes, there's definitely one over here.
It seems it's just.
Yeah, so there's one on the other side.
Thank you. But nice. Nice. Perfect.
Alrighty. So we'll get back to it in a moment. But of course, if you're curious, you want to walk through it already, go ahead, especially if this stuff is boring for you. So I was wondering how many people here are familiar with Python, comfortable with Python. Could you raise your hand? Oh, wonderful! Fantastic. Amazing. Great. Love it. For people who are less so comfortable, I have like a one slide, very short overview of Python that presents some basic data types, which is helpful. So the point is, I guess, that the data types are quite standard. If you're familiar with any other programming language, they probably exist there in one way or another as well. You have some simple data types for individual numbers, strings, and so on and so forth. You have lists and you have tuples. You have arrays that come from a separate library called NumPy. You have dictionaries, which are basically associative arrays, if that says something to people. But basically that means pairs of things. So if you have things that come in pairs, for example, a subject and a subject's ID, so subject name, subject ID, that would be a nice thing to put in a dictionary, because you need to create pairs of values that are always there together. An important thing about Python is list comprehensions. So that's something that really helps parallelize and speed up processes, and other things that apparently most of you are familiar with. There's a very basic couple of lines. The idea of Python is that it doesn't have a whole lot of built-in functionality. A lot of the stuff comes through outside packages, and the ones that we're going to need a lot today are probably NumPy, scikit-learn, I'm hearing also M&E, and for plotting, Matplotlib, of course, is one of the default libraries you go with. So I'm just going to skip that part, I suppose, unless there's somebody here who, I don't want to put you on the spot. But basically, we're also happy to share some links for more introductory tutorials for Python specifically. But I hope that for the purpose of the tutorial today, you are not going to need that, so we can just move on. So a couple more things about the Jupyter Notebook. It's going to be relevant for Colab?
Yes,
Wonderful.
still relevant.
Wonderful. So one of the ways to program in Python is by using Jupyter Notebooks. So these are really cool interactive things that I really recommend using. This is one of the primary reasons why people move from things like MATLAB to things like Python. The idea of the Jupyter Notebook, as you can already see in Colab, is that you have individual cells, and different cells can be either code, but it could also be text called Markdown, and through that you can create really nice interactive things, because you can combine in one piece code with images, with explanations, with logic of what you're trying to do with formulas. So it's really nice to use for teaching, but also for putting in your results, for making up demos, for your code and your analysis. So I really recommend this.
I'll make
Sure.
a small addition. In the notebook you have, you will also see some exclamation marks, which are similar to the IPython magics, but they are designed for the Colab environment. We use those to get our files and libraries, and if you're using any non-standard libraries like MNE in Colab, you will need to use those as well in your own code. Currently, please don't modify them in the notebook you have, because otherwise you will not have data.
Okay, thanks. So something Sam mentioned is called magics. So these are also these things, outside of Colab at least. So these can help you do certain things, like this one is very popular, allows you to plot inline inside the cells. And you can try out the other ones and see what they do. There are some helpful keystrokes here for switching between Markdown and code modes, for example, per cell. And again, we'll probably share some resources for some cheat sheets for Jupyter Notebook. Alright, so just before we go into a tiny break that is mostly there to make sure that everybody has their stuff running, I think we need to start loading the data, you said?
Yes. So there's going to be a couple of tiles here that you need to run in advance, and the first one is making sure that we have our libraries, because some of these need to be downloaded onto the cloud environment. And this one is fairly short, but once this completes, now the one I'd like you to leave running is this one, which will download the dataset for you. And one nice thing about Colab is that you can see which files are on here if you move to the directory tab on the side here. But yeah, this one will take a while, approximately 20 minutes, so we don't need to wait until it ends because we have some other stuff to cover, but 10 minutes is probably perfect.
Alright, sounds good. Alright, so with that we can take a tiny break and then start again at 31 minutes? Okay, around that time.
I'm Victoria Peterson. My name is
Hi, nice
to meet you when I said your name.
this is you. Yeah, oh yeah, no. So much. I'm so happy that we're here.
Of course. No, thank you for the invitation. Yeah. So you're thinking about making these, like, these events?
Yeah, a regular thing.
That's amazing. I have some material for exhibitions in the report.
I mean, we'll also be very happy to invite speakers to that.
No, I mean, because I always forget to put them in my slider. I mean, from the like cheaper, that would be really important. So yeah, I can share whatever.
Of course, and if you also want to do a tutorial, we're very happy to.
Yeah, we can think about that.
Yeah, wonderful. Thank you.
I'm sorry that I'm leaving, but yeah.
Of course, no worries. I mean, it's meant for really beginners. So perfect. Thanks, sister. I'll see you later.
Because I had to essentially rewrite everything to because there's no proper way to otherwise I would be like for reading bits by I think this is that everyone you fight not mainly
That's great. That's really hard that people don't have.
the exercises are fairly simple.
Yeah, it's just it's pretty
I want to leave time for Q&A.
We are from different universities.
We're missing some sections, so
Yeah, but it's Acacia University.
so
You need to put it
I have pretty much everything implemented up to classification. As we have. Actually, I this is well, the issue is now that I've distributed the GitHub icon. It's not going to add my changes.
Well, you know, it's good to put it up there.
No, I'll just add stuff as we go so that people can code with me. Because that's the best I can do. Oh, I am very stressed.
There's a little issue where recording is actually zero duration and only gets contains one sound.
That might be because the second one didn't contain anything. Oh, that's all. That should have completed in 3 hours.
So yeah, for limit was also the same. So yeah, you can have durations and
Yeah,
it's only one
so, can you show me the folder tab? So, go to EG matching thing.
Do you guys care for a second?
Sub 0 box. Oh, this has 6 files. Uh-oh. Okay. I guess I'll need to show this to everyone once they finish downloading, but delete the initially not the .1 one, the one before .1, because you want to keep the .1. Sorry about that. He got the data, but because there was already the initial data from the GitHub version, which is actually not data, but just a Git annex route.
Should we have deleted
replace
it?
that. Yeah, let's do that. Well, let's not do it yet here, because I need to show people how to do that.
So this needs to be removed? Or this one needs to be removed?
So this one needs to be removed and we keep the .1. but I need to show that to everyone, so let's keep the files here.
Yeah, it's still gonna take 4 minutes, but yeah, I guess we can kind of start.
Do you guys care if I'm like right there?
Not at all.
I just want to make sure the camera doesn't mess up.
It's alright.
Right, shall we restart? Okay. So, what? Nobody knows. So while the data is loading, we have a few minutes to talk about the modeling part. So in BCI, of course, our modeling is serves a very practical purpose. We just want to get something out of data. But in principle, in cognitive neuroscience, modeling has quite a big space in the field. And I cannot recommend you more to go check out Neuromatch Academy. They do great courses on modeling, on cognitive neuroscience, computational cognitive neuroscience, and deep learning courses. So one of the ideas that they start their course with is why model and what types of models are there. So they outline descriptive models which basically answer the question of what is in your data, how can you describe your data. Then there are mechanistic models which answer the question of how certain processes unroll or take place, and then they outline explanatory models. So why certain processes lead to the data that we have, or why do we observe certain phenomena in our data. So, like I mentioned, for BCI, our modeling is mostly very practical, so we just want to get best classification accuracy, for example. But if you start stepping outside of that and you need models to explain your data, for example, or to model a certain process, then you need to get into some more advanced topics, and that is something that we can also cover, hopefully, in our future tutorials. One of the most important things that they say in Neuromatch also is you have to pay attention to what is your question. So what do you want to do with your data, and what kind of data and model would be good for answering that question, and whether the data that you have at hand is actually suitable for answering that question. So we see time and time again that I don't know, a neuroscientist or a clinician, somebody comes up to us with the data and they say, oh, I just want to throw my data at some machine learning and get something awesome out of it. Or let's throw some data into a neural network and let it solve and learn everything. Well, I want to urge you kind of think about it, and I want to caution you against these approaches. I think machine learning is as good as your data is, and it really helps to explore your data first, to understand as much as you can about your data before you start kind of throwing it into different algorithms, especially things like neural networks. So yeah, this was just a word of caution on my side, and that's something we wanted to spend quite some time on today, on how to explore and visualize your data prior to starting to do any modeling. Right. So can we then go back to the practical side of things? Yeah.
All right. So if your data has downloaded, there's one quick fix that you will have to make. So if you go back to the folder structure that we mentioned and go into the Magic Pennies directory, we actually only downloaded the data for a single subject because, as you can see, the data set is huge. So we can't really download all 7 subjects. And in that subjects directory in EEG, delete the first EEG file you see, the one that doesn't have a .1 next to it, because that one isn't an actual data file. and rename the .1, which is the one you just downloaded, to be the EEG file. And once that is replaced, you will be able to continue. And let us know if you have any issues so we can fix it.
Is it something you need to do for each subject or just subject 5?
We only have one subject.
Can you please repeat which file has to be replaced?
Sorry?
Can you please repeat
Right.
which
So
file should be checked?
if you expand this area, you should currently have 2 EEG files. You need to delete the one that is .eeg without the .1 and rename the .eeg.1 to be .eeg only.
Thank you.
And if you weren't there when I mentioned at the start, we'll be using NumPy, Matplotlib for our plotting functions, scikit-learn for our main machine learning tools. Scikit-learn is generally the lightest of machine learning libraries, and it typically constitutes what's called traditional machine learning, which is most of the methods that were used before the current rise of deep learning. So this includes support vector machines, random forests, decision trees, and such approaches are still fairly effective in classification. And they are much faster to run than, say, a recurrent neural network. MNE we will be using for our data processing initially because the bits format currently is still being newly developed, and MNE provides some tools for reading those files. And it makes our life a lot easier to have it pre-processed for us. If you don't want to use MNE, that might be a bit harder, but I would suggest looking at the way MNE bids implements this, and then you can implement your own. But currently, within the MNE implementation, we go to the root directory that we saw there, and then we generate what's called a bids path. And this can be constructed based on the root path, and then our subject number, 05, the task, matching pennies, and in this case, data type and suffix are both EEG. This is because the file ends up being EEG and also the data type here. When it comes to EEG and MEG data, these will be the same. If you are dealing with another data type in your dataset, you might have a different suffix and data type, and you can look into the bit specification to find out what those should be.
Yeah, but in general, for a lot of time series data, including intracranial EEG, bits goes with these EEG, VHDR, VMRK files. So these are the brain vision format files, and that's again the benefit of using bits, because basically regardless of the brain modality, you're going to end up with the same files that you can process in the exact same way, which is really, really nice. And one more thing I wanted to mention about the bits, you can see a bit more how it's structured. So basically the file names are organized by having a meta tag. So this is stands for subject, then there's a dash and then the ID of the subject, underscore another meta tag, which is task, then the name of the task, underscore, and then it's either events or channels or electrodes or EEG. So again, a lot of structure in there on the meta level, which is really nice.
One thing that isn't included in this dataset that may show up in other bits datasets pretty often is that we only have a single session for each participant. If you had multiple sessions, you would also have, similar to the sub05, session tag in the folder structure and also the final files. And do we want to go into the file itself, or is that too much detail?
I think it's okay for now, so we can just move on.
So now we can just run this tile of the notebook. And M&E will do some analysis of the data. If you had it working correctly, it should show this 31-minute duration. If you had it show up as 0 duration, you might have run into some issues with downloading the data. So let us know if that is having any problems there. And as we can see, we have 10 channels with 2 of them being bad channels. And we have a sampling frequency of 5,000 Hertz.
Yeah, maybe we can go into the channels TSV so you can see that this information is there.
Yeah. So on the channels.tsv file, you can see that contains the type of the data, EEG, in units of microvolts, and it shows that some of these are bad because one contains high frequency noise and one wasn't in correlation with the other channels that much. The header file also contains similar information, but that is primarily, at least initially, part of the Brain Vision data format, which M&E already had compatibility with, so it extracts it from here most of the time. So afterward, let's try to get a sense of what the data here contains, and this is where we'll have our first task that you will implement yourself. And we are currently using M&E plotting function, but behind the scenes this is also Matplotlib. The visualizations would be interactive if you were doing it locally, but we can't really do remote interactive visualizations on Colab, unfortunately. And if we move here, you can see that we have 3 events within the span of the 20-second window that we put here. And we can see each of the channels with the bad channels hidden being visualized here. And one nice trick about Colab is if you mouse over each of these functions, you will be able to see what inputs these take, and most of the documentation will be visible here. So using that, try to implement these 2 tasks. The first will be to make the plots fit within our visualization, because as you can see, these are kind of overlapping because the bounds aren't very clear, and that makes it very hard to interpret what's going on here. So if you can change those bounds to fit within there, that will be the first one. And afterward, the M&E plotting functions also has built-in support for visualizing it with a bandpass filter. So currently, for the second task, I would like everyone to try adding a 0.1 Hertz high-pass filter, or you can also pick a frequency of your preference if you have your own high-pass filter choice. And we'll wait for a bit for everyone to catch up here and implement these tasks, and let us know if you have questions. Yeah, it might be running it low.
Okay. It's definitely still, still
Right. I guess it's kind of passive if it's downloading I think it's not that you didn't download the initial section, it's just it's showing you a root directory, which
Yeah.
is where it's downloaded.
So I was wondering where the actual file that she delete the non-point1 and then change the 6.1. I don't know where
Yeah, I'm not.
okay.
You could also go to runtime.
I love this change.
Yeah, be usually runtime. Currently, you can change runtime. It doesn't imply any chat. Oh. We'll have to
Okay, yeah, so then just make sure I don't do this incorrectly. Okay, so it's subject 5. EG. Subject 5, EG.
And
I delete the non, the one out. I change the one.
it's currently showing both. Because I think I'm loading one remotely.
Well, I stopped and then hotel.
That's what happens to make it feel as if don't make it
I just restarted.
line. Can you do like scientific?
Totally works.
Okay, so you think it's downloading the correct one?
Yes, because of the difference.
Okay.
Yes, so yours is also showing up. If you click on the dropdown, so there should be something there that says connect to host the joint. Well, there should be something that says remote or hosted.
In the top right. Like below your Google account. Do something.
What's the machine ID? One of the places where I have 2 tasks rather than 1, and the rest of the tasks are fairly simple.
So take just one line?
It's all online here. The first one is a little confusing if you haven't done it before. Alright, I'll start with a hint. So, a small hint for the first one, because that might be a bit confusing if you haven't done it before. you need to change the scalings, and that takes a dictionary as input.
Yeah. Oh yeah, it's very tricky. It's very like under the hood. You really have to watch your page and really just go wrong.
You will have to delete the exceptions for parts you have implemented, otherwise your code will not run.
Yeah, basically I'll put your directly on the side, and then you can find where it says. Try like running the first two cells. Yeah, so run that one. Because it won't like probably let you access the data until you read permission. Since it's like a not second half side code. Yeah.
Too much.
Alright, so okay, so
It's like David Potts.
Live trial in it. Live trial in it. Yeah, I like this one.
So what's that number? Is it a fraction of?
It's the absolute value of the maximums, I believe. Yeah, I didn't okay. As a quick note, if you reload, you will lose your password. So open the directory tab. So then
I should be inside here.
and go to delete the
So like I think this type is
and rename the dot one to be and try running the Alright, so now we will continue with the next section, and I will just show my versions of these two tasks. For the first one, I decided to use a 0.0005 4 by scaling. This is just the maximum value of the range, I believe. There will be a lot of trial and error in deciding what value you want to choose for these. And I think as long as you're in a state where you can see all of the data without it cutting to the top, you should be fine. And you don't need to care about the bad channels because they don't provide meaningful information. For the second one, I just added high pass equals 0.1 as the parameter, and that added a high pass filter. And you can see that one here. Although, because of the duration, that might be a bit difficult to observe, but it is still adding it here. So you can continue playing with these if you would like, but we will move on to some of the pre-processing. So now that we have the high pass filter visualized, if we like it, we can apply it. And behind the scenes, this one is a SciPy function if you used that one before. But M&E again has their own way of implementing it to work with their own data format. So now I'll run this, and we can also walk through the rest of the data. M&E also uses epochs, which are the data separated by each event in the marker stream. Here we are converting some of their events to be the same thing. So we are treating both of the raised left hand ones as the same event, and also both of the raised right ones as the same event, because we only want to classify between the left hand and right hand.
And the two events are matching the queue and not matching the queue?
Matching the queue and not matching the queue now. This is because of the original experimental design, but it's not a part of the experimental design that we currently care about, so we can just treat them as the same ID. And there are many ways of running the events from annotations function. I sometimes use custom function to give IDs, but in this case, because there's so few IDs, we can just do it with a dictionary again. And out of that, we get the events and event IDs, which is different from the dictionary we supplied, but we can then feed that to generate the epoch. Then we have the minimum and maximum time. This is in relation to when the event happened. And 0 seconds after the event happened, we start recording an epoch, and 4 seconds after events, we stop. So each of these epochs will have 4 seconds, which will be 20,000 samples because of the 5,000 hertz frequency. Then we can feed all of these into an epoch object to create the epoch, and finally plot it. And not sure what's going on here, but hopefully it will stop if I rerun it. Probably projector related. Okay, sure. So, besides the glitching, we now have the data separated into different epochs, and you might already be seeing some repeating patterns here in these 4-second time chunks.
Oh my god.
Maybe if you close the left window.
Maybe. Nice.
Ah, good.
Thanks for the fix. So, we are currently seeing 10 epochs here, and then we can start analyzing what's going on here. To do that, we take the data out of M&E by using the getData command, and that converts it from M&E's format into just a 3-dimensional array. And we can also get the marker stream from the events of the epochs. And we will look into the structure of these when we are looking into dimensionality reduction. But for now, we'll leave it there. And just as a small change to possibly get better results, the task for this section is to modify the above to include 1 second of recording before the event. And we'll go back to the slides for a bit after if you want to go over that part.
Sure, the next slide I think is about pipelines. Yeah? Okay.
Well, is that?
So,
Oh yeah.
what are you covering next? More cross-validation stuff?
Sorry?
What are you covering next?
So, for me, I'm currently doing the dimensionality reduction next. Did you have a stereotypical eigenvector slide here?
I don't think we did.
Okay.
We can easily edit.
Yes. Okay.
again, like the T-mean and the T-max?
So for the epochs, Tmin and Tmax are both relative time in relation to when a particular event happened. So based on when the events happen in the marker stream, and these aren't events with duration, these are just singular times, you can get the Tmin and Tmax in relation to that. So with the current setup with Tmin at 0 and Tmax at 4, those are 0 seconds after the event happened and 4 seconds after the event happened.
So let's say the event is happening at the first second, and I didn't understand like the T-mean. I understand Tmax like after once the event is happening, it's the 4 seconds after. So it's like segmenting it into 4 seconds. But what is T-mean? So let's say if we give it -1. So is it like -1 seconds before the event happened? Like
Well, it would be -1 seconds after the event happened, which would be 1 second before.
Okay, so it's always after the event.
Yes, in relation to after the event, yeah.
Okay.
So
And how do you
negative
decide,
gets you before.
and how do you decide the duration? Because I guess every analysis is different, right?
Duration would be Tmax minus Tmin.
So my question is, how do you? So for example, you're dealing with motor imaging signals.
Is there a way
Sometimes for classification, you can see the big typically some data that's useful before. So during the trial, that was fine.
Okay, so let's say I have like a duration of 9 seconds, and the event like we are talking about motor imaging, and the cue was presented at 6 seconds. So now that I complete the data, this is my this will be email, and this will be just as an example. But what if I want to have like a baseline, so let's say I need this. If I want to, let's say because it's 2 seconds, email -2, and then email that's what we're trying to do. So it won't this happens. So if I okay, so let's like
Oh yeah, of course.
and I'm interested in
Oh, yeah.
the entirety of the segment. So how do I get for email? Okay, so it's in regard to the events. Thank you so much. So technically you were saying like let's say my motivation is 9 seconds. And then you have to like analyze it for the entire 9 seconds. This is when the event is happening. This will be my baseline, which is like 0 to 4. And this will be like my comparison of what So what I do in my analysis is, I set my event at this, and then I talk, like I said, this and that, and then I have the event. So I'm slicing. When I make a file, and then I load it. Then I
Yeah, I'll just send it to you now. Oh, wow. The thing is, like, it's all balancing how much I don't really know. They seem to be oh, yes. Yeah. I think it's don't be on the website.
How much time do we have?
We still have half an hour, so maybe we should speed up.
I think we can do the slides after I do the solution for this. Oh, thanks. All right, moving back to us for a bit. The solution to this one is pretty quick. You just need to change tmin to -1 and delete the error here. And after that, you should have the tmin starting from a second before the event. And since we are moving on to some of the actual ML part after this, we also want to cover some theory after this loads. Great. So as you can see from the time points here, we now have it in 5 seconds. So let's also print these real quick to get an idea of the data. So after we've done this, we now have a marker of 300 trials, and the structure of the other one is 300 trials, 10 channels, and 25,000 total samples over the 5-second duration. So now I'll pass it back to Julia to cover some of the ML.
Yes. Yeah, I'm not sure if you can technically call it ML, but what we want to start out with is a very simple transformation on the data that you can have. So something called dimensionality reduction is a very common type of transformation in EEG data or any other kind of brain data, because you typically end up with lots of data points or lots of channels, and we want to reduce that amount to something that we can work with, that's more handy to work with. Oh wow, these colors look terrible. Anyway, one of the very popular ways to perform this dimensionality reduction is called principal component analysis, and I'm sure you've either heard about it or used it in your work. Just a brief recap what it is, what the intuition behind it is. Basically, imagine you have. So I'm going to do the dimensionality reduction over channels or over time.
Over channels.
Or channels. Okay. So imagine you have two channels in your data set. So on the axis X, you'll have data from channel 1, and on the axis Y, you'll have data from channel 2. And you plot them together with this scatter plot, and you see that there's clearly a relationship between these two. So what you can do is you can take this whole cloud of data and basically rearrange it, so transform it in a way that captures the amount of variance in your data and orders different components of the data by the amount of variance that they explain. So if you look at this cloud of data, of these cloud of data points, you'll see that in this two-dimensional example, there's clearly this dimension of variance that covers the largest amount of variance. So these would be, after the transformation, the first component of the PCA, because the amount of variance that can be explained by the data goes all the way from this corner to this corner. So this basically covers the largest spread in your data. And the direction of the largest spread will become the first principal component in your data. What happens next is that we need to find the second component because it's a two-dimensional data, and the second component will be orthogonal to your first component, and it will cover the second largest source of variance in your data. So this spread is much smaller than this one, therefore this would be a second component. And what you could also do is plot all of the components on your data and how much variance they explain in your data, if you have more than just 2 channels, but say 10 channels. And here you see that each component would cover, the first component would explain about 30% of variance, maybe 35, this one 21, so you see that they are ordered nicely. The first one explains the most. And you could also plot the cumulative amount of variance that they explain. And the data dimensionality reduction part comes from the fact that you typically can select a number of components that explain up to, say, 90% of all of the data. So you can only use, in this case, say 5 principal components that transform data to capture almost all of the variance in your data and only work with these 5 dimensions rather than all 10 dimensions. Alright, so that's a bit of an intuition, and next we're going to apply this to our data.
And just as a bit of an extra, dimensionality reduction is typically considered an unsupervised learning method. And that's because to perform this, we aren't even going to be using our marker stream. We only need the original data. But there are a few methods that are supervised dimensionality reduction methods, like linear discriminant analysis. In my experience, they don't provide that much benefit because PCA and other methods like independent component analysis are already quite powerful. And there's one small change we have to make here because we just changed the size of the data. All right. So now we have to reshape our data because scikit-learn is not designed to deal with large time series. It can only handle data in 2 dimensions. So in this case, we have to collapse our channels and time series, so all of our samples together. And that ends up with 250,000 data units? Yeah, parts. Data. So based on that, then we can apply our BCI, and that will reduce all of the data in each trial into something much smaller. And as Julia mentioned, you can look at how much each of these components is covering in the data based on the variance included by it, and you can also regenerate your data to look at how it looks like by using the eigenvectors.
Does it apply normalization by default?
Sorry?
Does it apply normalization by default?
This one I don't think it does. And there's multiple ways of doing this, but here we'll be dividing into components based on the number of channels, so in this case 10. You can also do it by other numbers, and your task here will be to do 9 components, which is channels minus 1, which is also sometimes used as a standard approach. And again, you can just modify the code above to make that happen.
Yeah, maybe if some people are ahead, feel free to plot the variance plots to see how much variance each component explains. Just play around a little bit with best numbers, what is the best number of components to go forward with. Play around with the parameters of the PCA, look into what are the options.
Scikit-learn also has a method for inverse decomposition if you want to look into that and play around with the eigenvalues and eigenvectors more. Let's move back to theory, so that we can still cover our BC.
Sure. If you want to do pipelines, we can also skip pipelines. Maybe just go to SVM.
Yeah, skip pipelines
Yeah.
and go to
So,
SVM. Let's also cover everything pretty much on your slides, so that we at least have that side done.
Sure. It's just there's only 20 minutes left, and I think SVM may take 20 minutes.
Let's try to simplify. And I think there's some stuff in the neural network part that I'd like to show.
Yeah, exactly. To cover these both, that's skip pipeline.
Yeah. I think let's just continue for now because this is fairly
sure.
easy.
Yeah, just go ahead. Okay. All right. So
Mike.
Yeah, so while some people are finishing up, I think that was generally a pretty easy task, so keep working on it if you need to. But in the interest of time, we wanted to go ahead. So the next thing that we're going to cover is the proper classification method. So that's the classical machine learning we were talking about before. And the one we're going to go over today is the support vector machines. Again, I just want to give you a very basic intuition. We're not going to go into a lot of math in any of that. So support vector machine is a pretty robust method to perform classification. So it's perfect for tasks when you have
a bunch of brain data and labels. For example, in this case, you have right hand and left hand movements, and you want to find the mapping between the brain data you have and those labels. Support vector machine is one of the methods that will allow you to do that. It's a non-probabilistic, originally non-probabilistic approach, so it doesn't give you probabilities of which class label to apply to each epoch of the brain data, but it will just give you the label. The way it works is basically summarized over here. Say, again, in a simple example, you have only two channels or features that the classifier works with, and this would be on the axis X would be feature 1, on the axis Y would be feature 2. So it's either channels, or it could be PCA dimensions, or it could be any other output of any other transformation that you perform on your input data, which in our case is brain data. And again, if you plot all the different data points across these two features or EEG channels, you will see that the data points labeled with blue would belong to one class, and the data points in green would belong to a different class. And in this case, we have a very nice separable problem where it's possible to separate the two clouds of data into two nice subclouds. What happens here in this very simple two-dimensional example is that we basically draw a line between the two, and around that line we have what is called a margin. The way support vector machines work is that they try to fit in that line in such a way that maximizes the distance between any two data points that come from two separate classes. So in this case, drawing a line this way maximizes that distance the most. So these two would be the closest examples from two different classes, and this distance between them would be the maximum. So for this simple case, our support vector machine results in basically drawing that line, whereas for multi-dimensional cases we have multiple features, so multiple PCA components or multiple channels that you work with. This will become multidimensional, and you will be fitting something called hyperplane instead of just a linear line. But the idea behind it is the same. You still try to maximize the distance between data points that belong to two different labels. So by design, support vector machines work with only separation of two classes. So it's a binary classifier. However, you can build extensions on top of that using one of these two strategies, either 1 versus 1, where you just fit in separate multiple SVMs to separate each pair of classes that you have. Or there is a strategy called 1 versus all, where for each class you learn to separate that class versus everything else. And both of these strategies are implemented in SVM, in scikit-learn, so you don't have to worry about it yourself. You can just use the existing implementation, and it will handle multiple classes just as well as two classes. Alright, and next we're going to get into that, I suppose.
Let's cover the neural network part as well before
Alright.
we switch.
Okay, so Tanya's telling me that you'd like to cover up the slides.
We are running out of time, so we want to cover the theory at least.
Alright, so one more thing that would be handy to mention in the context of classification and machine learning modeling is overfitting and regularization. So what happens is, imagine you have this kind of problem. So the underlying data points are the same in these three graphs, and we're looking at the classification problem. So we have two types of labels, blue and red dots here, and we want to train a classifier that learns to separate these two. So given new input data, it will provide a label, whether it's a red dot or a blue dot. And the interesting thing here is these are results of three different classifiers, three different classification models. One of them is doing something called overfitting. So overfitting
provide you with a very good separation. So if you look closely, you can see that this wiggly line actually separates the two classes perfectly. So the two classes are completely perfectly separated, and on your classification training set, you will get perfect accuracy, because all of the labels that are supposed to be red will be labeled as red, and all the blue ones will be labeled as blue. It's a perfect classifier. The problem with overfitting is that because this is a very complex wiggly line, it means that the model has a lot of complexity to fit this complex line. It's much more complex than just a straight line. And what will happen is that most likely in your test set, so the new data that your classifier has not been trained on, you will likely end up with a point that will be misclassified, because the model is very complex and it just fits to the variance of the training set way better than it could ever be applied to the test set. That is going to have a different distribution and different variance. So a model next to it has a decently good fit, because it is a less complex model. So yeah, fitting a line like that is much easier. Yet it does contain some classification mistakes. So you see that some blue dots end up here and some red ones end up there. So it will not overfit on your training data. It will not give you 100% accuracy. But to compensate for that, it will probably have a much better performance on the test set. And on the right side of that is an underfitting model. So this is the simplest model you can build, because it's just a line, and it underfits quite a lot, because it doesn't really pick up on the distribution of the red dots, which is a lot more like this, right, rather than just a straight line like this. So it will result in a lot more error in both the training and test sets. So the examples below show similar examples for regression, where the task is not to separate two different labels in the data, but to fit your data. So just explain, to provide a function for your data. Again, this one is overfitting, this one is probably the right fit, and this one is underfitting. So basically what we're looking for is the best fit in all of the models that we are working with. And the way to find it is basically by trying to find the trade-off between the errors in your training and test sets. So your training set is the data you train your classifier on, and your test set is a separate data that your classifier has not seen that you use to validate the performance of your classifier. So ideally you want to be somewhere here where the distance between these two types of errors is minimal. So yeah, the way to do it in many applications, especially in classical machine learning, is by using a technique called regularization. So regularization is an additional component that you add to your classifier that helps you combat that situation, and it basically controls the complexity of your model. One of the easy examples is over there. So basically you have, so this is an objective function that your classifier is trying to minimize when it's training on the data. So it's trying to learn to minimize the error of classification. And a component here that does regularization is this. So it's some kind of a weight lambda usually, and a function over your data. Usually it's a function over the weights of your classifier. And typically regularization just tries to push your weights, the weights of the model to be very small. Or, depending on the type of regularization, to be, for the weights mostly to be 0. So that it imposes a so-called sparsity constraint on your weights. Again, you don't really have to worry too much about the math underlying this, because in scikit-learn you have a parameter called C, as far as I remember, that helps you introduce this regularization to your model. And you can play around with it, I guess in the upcoming bit.
and change the value of the parameter C from 1, which is default, to higher or lower values, and see how it affects your model, how it affects the performance on the training set as well as the test set. And I'm curious if you'll be able to find an optimal value for your regularization. Typically, you would divide all your data into 3 types of sets: train set, validation set, and test set. Then you use the train set to train your classifier. You can use a validation set to identify the best hyperparameters of your classifier, and in that case this would be the regularization parameter, so the one that controls this component. And then the separate test set you will use just to show what is the performance of your classifier on this completely untouched separate bit of data that was not used in designing of the classifier. All right, well, shall we move on with the SVM rather than the neural networks? Because I think if I talked more, we'll run out of time.
I guess one thing I wanted to show on the neural network side, since we definitely won't be able to cover it in the code section, is I would encourage everyone to go to the TensorFlow playground to get a better intuition of both the regular, both the regularization and how neural networks work. And here you will be able to modify all of the parameters you want, your regularization rate, and also what type of regularization you will apply. So going back to the code for the last 5 minutes we have, we can move on with classification, and you should have finished doing this change. So now after you have your PCA data, you can then feed that to your SVM. And because we don't have time, I won't do the train test split here. But we did have it imported here if you want to play with that. And you will find that in a lot of cases the most important functions in scikit-learn are these fit and transform functions. If you wanted to use a split data, then you would fit to your train data set and then only transform on the test one. Let's see what name I gave here. Okay. Oh. Okay, so for our last few minutes, I just wanted to give some ideas of where to go from here. Something we didn't cover is in scikit-learn you can also build pipelines to do all of these steps together. This can help a lot if you are separating your data into different parts or you want to run multiple processes on similar data sets. yeah, you can look up the pipeline utility for that, and every single model in scikit-learn is designed to work with them. You can also optimize your hyperparameters in more adaptive ways by using grid search CV. So I would also mention that you might want to look that up. And finally, if you like scikit-learn, but your only issue is I have so many useful time series properties, you should look up tslearn, which has similar abilities, but is designed to work with all of the scikit-learn structure, while still being able to process what the three-dimensional data that we had here.
So what's the final performance of this VM?
I don't know.
Can you print the hashes?
I forgot what the fit transform replacement was, but yeah. I don't think I can because
Yeah, you can transform separately.
yeah. This is where the panic gets in. What was the SVC replacement for transform?
Do you have help for that?
This is where Collab's autocomplete doesn't work.
Weird. Oh, it's predicted.
Predict, yeah. Yeah.
And this classified score or something.
Print. Underscore, underscore, score.
Excellent score. No. So, yeah, you just want to predict.
Yeah. Yeah, you need to feed them to the actual score.
Ah, excellent. What a great classifier we built.
Yeah, wonderful.
Is it good? Yeah, it's excellent. Yeah. Well, yeah, when I fill in the file. But this is like training set.
Yeah,
Why would it be so long?
I don't know. This is my last minute prepared this one.
All right. So we can see that we built a great classifier, and we'll challenge you guys to do a much better job. Things to try out, I would recommend is normalize the data, try some other transforms, see whether the BCI that we built here is the best, play around with parameters. All right, so we thank you again for deciding to spend the opening of the meeting with us. We're very happy about the turnout, and we'd love to continue with our tutorials. So please give us some feedback and some suggestions about topics. We'd love to involve you in that process. Thanks a lot again.